All right, we shall begin. It's Monday. Happy Monday, week 5. Time is ticking along. I imagine you guys are in the midst of midterms and whatnot. If you don't have a midterm this week, you might have had one last week, or you will have one next week, or something like that. We have an exam, but that's coming week 8. I don't know if we you even. I don't think you can call it a midterm in week 8. Certainly not week 9, but I don't know. That also exists, right? There's like tests during week 9. But anyway, just in case you need just I don't know. I want to say a loving reminder that your grades do not define you. Of course, we want to get good grades, and of course, it feels good, and we should do our best and everything. But at the same time, like you as a person and your contribution to the world is not just your academic excellence. Okay. I want to talk a little bit about our final project. So everybody should be assigned to a group, and I'm not sure if you are familiar with the feature on Canvas. So I don't have it on here because I'm not part of a group. But over on the left-hand side of Canvas, under courses, there's going to be a little button called Groups. Okay, and everybody should be assigned to a group. Hopefully, it aligns with. I think I did it right, but if I messed up, let me know. Okay, but if you click that, it should have a little group listed there, and within the groups page, you can kind of make announcements to each other. There's like a discussion section. I mean, you can also use email and whatnot. But yeah, having that can be helpful. I hope everybody in your groups and everything responds. And if you have any trouble with communicating to certain group members and things like that, you can let me know, and I don't know, send an email. Sometimes when someone gets an email from their professor, it feels a little bit more urgent. I don't know. And then anyway, I want you to sign up for a proposal time slot. So I'm hoping I can do everything on Thursday, and I know everybody has class on different days and stuff like that. And so I've kind of blocked off my whole Thursday from 9 a.m. to like 7 p.m. And so hopefully there will be a time slot that works for your group. I'll allow up to one person. Like, if you can't find a spot that works for all 5 of you, maybe there's a spot that works for 4 of you, and I'm okay with someone being missing from the proposal meeting. But if everybody can make it, that's better. Do that, and if the times come and you guys aren't ready, then let me know. But or you can't find a spot that works, you can let me know. All right, let's see. So we're gonna start to shift gears a little bit, and now we're gonna start talking about how we can think about data, how we can kind of draw conclusions from our data, and things like that. A lot of the beginning part was introducing a lot of the toolkit in terms of this is how we graph things, this is how we calculate summary values, this is how we, on Friday was like how to pivot the data and things like that. And those are all going to be very important for you to be able to interact with your data. Okay. But the real big purpose of why we even want to interact with data in the first place is that we want to draw conclusions from it. And what kind of conclusions you are able to draw from your data very much depends on how that data was collected and how reliable that data is. And so this is something we want to start talking about. And so in today's lecture, there's no code. Okay, maybe that's going to be our first, other than like the very first day where I went over the syllabus, it might be our first lecture that doesn't have any code in it. But it's going to be a lot of kind of ideas and things that we need to think about as far as talking about our data. Okay, so yeah, all right, blah, blah, blah. This is what we're going to be looking at. Okay, so yeah, the big idea is we want to draw conclusions from our data, okay? Or statistics, data science, all of this is about learning from the data, and in ideal situations, we are able to learn something that helps us make good decisions, okay? Basically, when you use data to make your decisions, those are going to be more reliable, have better outcomes than just kind of going off of gut feelings or tradition. A lot of times tradition aligns with the data, and that's how that's why they're the tradition kind of developed in the first place. But sometimes there could be a shift in how things work, where the old traditional methods no longer apply, and having the data to kind of back that up and back up that change to say, hey, this used to work in the past, but if we pay attention to the data, things feel like they're shifting and things like that. Okay. Yeah, I write. We live in this golden age of data, where we have. I think I probably talked about. Did I talk about this on the first day? Also, maybe living in this golden age of data. Yeah, so much we can use data, use that, and it's great. But there's also a lot of people claiming to say what the data says, and it's not really what's saying that. Okay. Anyway, as far as we're talking about the data that we have, a lot of it is kind of passively collected. Okay. And then other times we set up an experiment to try to collect the data, and how we're getting our data will affect what we can kind of draw from it. Okay. Every time when we draw conclusions, generally we want to draw conclusions about a population. Okay. So every time we have a question, right, a research question, something that we're curious about, there implies a population, and the population would be everybody relevant to that question. Okay. The problem is that the population is just too big for us to study directly. Okay, so if we're talking about some kind of political poll, the population is everybody who's going to vote. Okay, and that's a lot of people. There's like millions of people, and so if you want to get any kind of like predictions before actual election day, you got to conduct polls and surveys and things like that. And you don't have access to all millions of people, but you might survey maybe a few hundred, 1,000 people or something like that. Okay. So instead of looking at the population directly, okay, we study a sample, and based on the sample, we make inferences to the population. Okay. So the sample is the subset that we actually get to observe, right? And yeah, so we use the sample to learn about the population. And you hear these terms, bias and variance, and they show up in all kinds of different places, okay? So like in machine learning, we'll talk about bias and variance. But we also run into this problem of bias and variance as far as sampling goes as well, okay? Bias means your sample doesn't look like the population, okay? So, if you conduct a survey among your friends, right? Among all of your friends and something, that you might all agree, have a shared opinion or something like that. And then if you say, well, everybody I talk to feels this way, therefore the entire country should also feels this way. That's not going to work, right? Because you have a biased thing. Okay. The other part is variance. Okay, variance refers to the idea of how much your estimate changes across repeated samples. Okay, so you could just imagine, like if you flip a coin 100 times, you're expecting something around 50 heads, 50 tails. But because it's random, maybe you get 53 heads and 47 tails. Okay, if you flip a coin 100 times again, maybe you get 45 heads and 55 tails. Okay, so the fact that one sample ended up 53% heads, another sample ended up 45% heads. That reflects kind of variance, okay? If you have a small sample, in general, you're going to have much more variance. So if I flip the coin only 10 times, I might get 5 heads and 5 tails, but I could get 7 heads and 3 tails. I could get 4 heads and 6 tails. And so in that case, you might have a sample that's 70% heads and another sample that's 40% heads. So you have a lot more variance there, and that's because you have a much smaller sample. And the same kind of thing happens when you're doing surveys and stuff, okay? So when I say often caused by too small a sample, I mean like maybe problems related to variance. Okay, there's always going to be variance. Variance cannot be completely eliminated, and bias can't be completely eliminated. But problems with variance, I should say, are often caused by too small of a sample. Okay, so just some examples of in terms of like populations and samples and things like that, right? So just some potential research questions, right? So is some new drug ABC, is that going to be effective for treating disease XYZ? So, and it doesn't even have to be drugs, right? It could be like, oh, is this supplement? You know, if I take these, I don't know, there's like, you go down certain aisles of the store and it's like protein, this supplement with protein and this thing and this thing, and this is going to give you better energy or improve your brain performance, or, you know, this other kind of performance and whatever. And it's just, does that work? Right? So the population would be kind of everybody who might, at least for a treating of a disease, will be everybody who has the disease, okay? And that population, it's too big, okay? And we can't track it down. What do you call it? Health records are private, right? So, you know, let's say you want to know, hey, is this a reasonable treatment for, I don't know, IBS or something, okay? Who has that, all right? Nobody's gonna, you can't, there's no database of everybody with a certain disease, okay? You know, so tracking that down, there's no way to get track down that population, okay? So at best, as far as the sample that you actually get to work with, you have to kind of tell doctors and say, hey, there's a study going on. If a patient, you know, fits the criteria, can you just let them know the study exists? And maybe you get some volunteers. But yeah, you're going to be dealing with, you know, a much smaller sample. There's no way to track down the entire population, okay? Other things, you know, can we increase the price of a product by 5%? Are people still going to keep their subscription, or are they going to cancel, right? So it seems like every streaming service, it's like every couple of years, it's like, all right, the monthly cost is going up by $1, and they're trying to figure out kind of price sensitivity to these things. So the population is everybody who might be a current customer, and people who aren't but might consider things like that. What do you actually get to work with? You know, there's going to be some kind of focus group, right? You have to identify people who you can kind of talk to, things like that, right? In politics, the question is who's going to vote for, you know, name some candidate, okay? All right. And the population would be kind of everybody, you know, if you're talking about a senator, it's like everybody who lives in that state, okay? Or, you know, congressional district, everybody in that area and things like that. And as far as like polling and surveying goes, it's going to be, you know, the likely voters interviewed. So all of these things, we're hoping to go from the sample that we have and to try to draw conclusions about the population, okay? And this is hard, okay? As far as how do we gather our data, kind of the primary sources that we can really use are observational studies and controlled experiments. Anecdotes exist, but we don't really have methods to work with it, right? So anecdotes are basically stories, testimonials, and they can be useful anecdotally, but we can't draw any kind of valid population inferences. So basically, every product review is an anecdote, okay? You go on Amazon and you read about the review of the product. That's someone's personal experience, right? A restaurant review is someone's personal experience, a review of a teacher, things like that in a movie. These are all just anecdotes. They can be useful. We can kind of aggregate them, like the Rotten Tomatoes score takes a whole bunch of reviews and tries to calculate an average. When you go on Amazon and you look at products, it takes a whole bunch of reviews and tries to calculate an average. But you've probably had this experience where you go on Amazon and you see a product and it's got like a 4.9 rating with 12 reviews. And then there's another product with a 4.6 rating, but like 15,000 reviews. Okay. And then, and it's kind of hard to, like, which one's the better product, right? And probably you've had the experience of also you read reviews for a restaurant before you go, and your experience at the restaurant is different from what you expected based on the reviews. Either the restaurant didn't live up to your expectations, or based on the reviews, people left like a 1-star review for something. I mean, people who write reviews online, there's all kinds of different things, right? Most people's experience with a product is probably average, but if you look at reviews for products, there's generally kind of this bimodal distribution of like 5-star ratings and 1-star ratings, and you don't have a bunch of 3-star things because, well, our review society is like, I don't know, like if you take Uber or order with DoorDash or something, and if you leave anything other than 5 stars, it feels like you are greatly insulting the person, right? Even if it was just like met expectations, right? And also unfortunately that's also happened with like grades in terms of like, now we're at a point where anything less than an A feels like I didn't do well or something. But how do you anyway? Okay, so anyway, anecdotes. We don't have statistical tools to deal with anecdotes. Okay, but we can have observational studies. We can have controlled experiments. With observational studies, researchers observe. As far as the subjects that we're studying, they self-select whatever behaviors or the treatments. Okay, so people make their own decisions, and we're just kind of observing. Okay, and if you have an observational study, we can make estimations of associations. Okay, we can say like, all right, this variable seems to be associated with this other variable. Okay, but there could also be what we say confounding effects. Okay, and I'll explain this. But basically, because of confounding effects, we can't make cause and effect conclusions. We can't say one thing causes another thing. And so this is something to be mindful of and cautious of as far as when you do your group projects. Okay, every group always wants to ask the question, what variable has the biggest influence on this outcome, right? What variable influences this, okay? But that word influences or has the impact on this, that implies a cause and effect relationship, okay? Because it's like, what is causing this other thing, or what is influencing, or what impacts the other thing? And most of your data is going to be observational, okay? Most groups data that you're going to be is going to be observational. Some groups might come across experimental data, okay? But most people's data that they're looking at will be observational. And so at best, you can just make kind of statements of association, and you can say this seems to be associated. Okay, and yeah, I'll detail this. Okay, we have controlled experiments as well. In a controlled experiment, the researcher will assign the participant to a treatment group or a control group. Generally, ideally we use a random situation there. We use blinding or placebos. And if it's a good experiment, big enough, then you can draw cause and effect conclusions, okay? All right, before I forget, let me give you your first view quiz answer. The letter E. E as in elephant is your first view quiz answer, E. All right, so sampling is this process that we use to select individuals from the population to study, okay? Ideally, a sample is representative. A representative sample means it's like a miniature version of the population, okay? It's like if the population has a particular gender split, then your sample also has kind of a matching gender split. If your population has certain age groups and certain proportions there, or certain nationalities or things like that, your sample, whatever you're looking at, kind of reflects what the population looks like, okay? A sample is biased if you have too many or too few members of certain groups, okay? So it could be age groups, it could be gender, it could be region, nationality, racial groups. If you've got too many or too few from a particular demographic group, then we say your sample is biased, okay? Biased here doesn't necessarily mean there's malicious intent, okay? It just means the sample doesn't look like the population. And there could be malicious intent behind the biased sample, but it's not necessarily that, okay? A lot of times when we hear bias, we think like someone, there's prejudice or something, and it's not necessarily that, okay? In a lot of the math that we use behind statistics and things, so when you take math 170S or whatever, stats 100B, there's a lot of the theories and the depend on an idea of a random sample, okay, a simple random sample. And in practice, it's actually really hard to get a true simple random sample, okay? So a simple random sample needs what we call a sampling frame, basically a list of every single individual in the population. This is almost impossible to get in real life, okay? Unless you're doing a simple random sample at a single institution, like maybe at an elementary school, you can get a list of all of the students enrolled. That probably exists. But if the population is all elementary school aged students in Los Angeles, that's really hard because you have those enrolled at perhaps Los Angeles public schools, but then you also have those enrolled in private schools, those enrolled at, those who are homeschooled, and those who might not be in school at all. And so once you go outside of one kind of institution, then it becomes really, really, really difficult to get a true sampling frame that lists everyone, okay? But let's say you do have a good sampling frame, then you just select individuals at random from that sampling frame. Every individual in the sampling frame has an equal chance of selection. Every possible sample is also equally likely. So like lottery numbers, okay? Every single combination of, I don't know how many numbers are on a ticket, 6 numbers or something. It's like every single combination of 6 numbers are equally likely. 1, 2, 3, 4, 5, 6 is just as equally likely as 11, 25, 17, I don't know, whatever, 6 numbers, 6 specific numbers, every single combination equally likely. It feels kind of crazy, but That's how it goes, okay? Simple random samples tend to be representative, okay? Just mathematically, there's no reason why it shouldn't be, okay? But it's random, so there's no guarantee that it will be, okay? There's no guarantee that it is representative, okay? And so if you are able to do randomized treatment, as in an experiment, you can make cause and effect conclusions, okay? We might call this internal validity. If you are able to do random sampling, okay, or probability sampling, okay, then that supports the idea of generalizing your conclusion to the population, okay? External validity, okay? And in the ideal scenario, we can have both, but in reality, we almost never have both, okay? In reality, at best, you get one or the other, okay? And in a lot of cases, you get neither, all right? So yeah, in some fictional scenario, we get both, but this is almost never the case, because as far as experiments go, especially if you're working with people, you need consent from the participant to be part of your experiment, and not everyone's going to consent to be in your experiment. And then as soon as somebody says, I don't consent, you no longer have a random sample, okay? Because, so having both is almost never, okay? So you have to make a lot of assumptions to kind of fill in the gaps, okay? So as far as, drawing cause and effect conclusions or generalizing to the population, okay? We want to know, like, does one variable cause another, okay? And as far as causal identification, as far as it goes, it just applies for the units, the individuals that you studied, okay? Does X cause Y for that? And this is kind of, again, so many groups want to say, hey, what variables impact this? Okay, what variables influence this? And that's another way of stating which ones have the greatest kind of cause and effect relationship, okay? But it's actually kind of hard to do, all right? Generalization, though, is like, hey, if this is the relationship I'm seeing in my sample, can I generalize it to a population, okay? So again, randomization with an experiment helps with causal identification. Probability sampling, random sampling helps with the generalization, okay? Sorry, there should be I don't know how to draw lines. Okay, so if you have a random sample and random treatment, then you can draw cause and effect conclusions and generalize. Almost never, okay? So random sample, but no random treatment, then your relationships will generalize, okay? To draw any kind of cause and effect conclusion, that requires big assumptions, okay? If you don't have a random sample, but you do have random treatment, then you can draw cause and effect conclusions, causal relationships for this particular sample, but you can't generalize to the population, not automatically at least, okay? And if you have neither, okay, not a random sample, no random treatment, then all you can do is you can draw associations for this sample only, okay? Drawing cause and effect conclusions require a lot of kind of assumptions or design implications. Generalizing needs information about the population and probably weighting to adjust things, okay? All right, so let's just go through a few examples and a few kind of concepts here. Okay, so is drug ABC more effective than conventional treatment for disease XYZ? The population there would be everyone with the disease. And again, impractical or impossible to measure everybody. So you get volunteers with disease XYZ, okay? In an observational study, okay, what we would do is we would compare the outcomes by what the patients chose or received. So it could be, the patient talks to the doctor. The doctor says, okay, I'm going to give you this medication or something like that. And you look at the results, and all you can do is you can draw an association. And this could get complicated because the doctor may end up only recommending this treatment for some of the patients, okay? So, I don't know. So, there might be like known interactions or something. So it'll be like, okay, if the person is already taking these other medications, don't prescribe this drug, okay? And in that case, now you're missing a certain segment of the population. And so if you observe differences in the outcomes, is it because the drug's making a difference, or is it because of this other factor going on? Okay, so all you can do is kind of draw associations there, okay? And if you are able to conduct an experiment, okay, then you randomly assign your participants to either receive the drug or control, all right? And you kind of ignore everything else, which might not be possible, okay? And then in that case, you can draw a cause and effect conclusion, okay? All right, so here's another example regarding like limitations as far as observational studies. So, maybe you get information regarding app users, right? So you're working at a company, the company releases an app, and in the terms and conditions you say, hey, we're going to collect data from the users, right? That's probably every single app that you've downloaded, right? So they're tracking app usage, and they want to know, like, okay, who's still using the app, okay? Like some kind of game, right? A lot of times you download a game and it holds your attention for a few days, maybe even a few weeks, and then you stop kind of playing with it, right? And so they say, we observe that users who enable notifications on the app use the app longer than those who don't, right? So every time you install the new app, it's like, can we enable notifications and things like that, right? And so this is kind of like, so you go, oh, we should really push for notifications or something like that. But you can't actually draw a cause and effect conclusion because you have these things, right? The user who says, yes, allow notification, okay, right? That might be related to how interested they are in the app in the first place, okay? So more engaged users are more likely to turn on notifications in the first place, okay? So that could be the thing, right? There could be other confounding effects, right? That affect both whether somebody enables notifications or not, right? Like prior usage. So if somebody had used this app before or something, and they go, oh yeah, I definitely want the notifications or something, that could drive it, and that could also be related to the retention of the user. So all we can say is, yes, there is an association between notifications and retention, but we can't draw the conclusion that notifications cause or drive or impact retention, okay? And yeah, there is right, the flip side, the reverse causality is also a possibility, right? Users who are intending to stay, they might be the ones that are more likely to enable notifications and things like that, right? So this is association, it's not causation. We can't do that, right? So we can report an association. Opt-in users, people who opt into notifications, end up retaining more, but we can't come to the claim that enabling notifications causes higher retention, okay? Without some kind of experiment that addresses this. Okay. With a controlled experiment, we might be able to draw a cause and effect conclusion, and the way it works goes something like this. Okay, wait. Let me give you. I've given you just one answer so far. All right. Second view quiz answer is the letter B. B as in bear. B as in bear. Okay. So we want to know, all right, how much does this drug affect recovery from a disease? Okay, and we want to get the kind of the cause and effect relationship there. Okay, so we get our participants, and then we randomly assign them to either the treatment or the control. Okay, our placebo, right? The patients shouldn't know whether they are getting placebo or control. Okay, so we say our patients are blind. Okay, and evaluators are also blind. So what I mean by the evaluators are, some things are easy to measure, like weight. You just have the patient stand on a scale, you get back a number right away. Okay, but other things are harder to measure. Something like depression. Okay, and so is someone's symptoms of depression improving or staying the same or getting worse? That requires the person talk to a psychologist or psychiatrist. The psychologist asks questions and says, how many times in the past 14 days have you felt like this and things like that. And based on that, the psychologist makes an evaluation and says, okay, your symptoms are improving or your symptoms are getting worse or things like that. And so if there is somebody making an evaluation, we don't want that person to know, oh, the patient's receiving placebo or the patient is receiving the medication, okay? And so if the patient doesn't know and the evaluator doesn't know, we say that's a double-blind experiment or things like that, okay? So anyway, the idea here is that at the start of the experiment, okay, because we've randomized who gets treatment and who gets placebo or control, okay, our two groups should be statistically similar, okay, both on things that we've measured and things that we don't know, the confounding, if there are confounding variables and stuff like that. Because we randomize them, group 1 and group 2, there's no reason why these should be different, okay? So if we do see a difference in the outcomes at the end of the experiment, right, we find this group improves and this group didn't improve or something like that, okay, we can say that difference can be attributed to the fact that this group got the medication and this group was control, okay, because at the beginning everything was kind of random, right? So because everything was kind of the same on average at the start, okay, a difference in the outcome at the end of the experiment can be attributed to the treatment assignment, okay? All right, I gotta quickly kind of blast through these things, but the reality is a lot of our data that we have, especially if we're downloading data from, logs or some kind of, platform app thing or sensors or streams, these are almost never going to really be a random sample, right? And it's a big assumption and probably a wrong assumption to treat them as if they are representative of the population, okay? Having lots of data reduces kind of the variance issue, but not the bias. And so you can kind of get some very wrong, very precise, but wrong answers if you have a lot of data, but it doesn't look like the population, okay? And so anyway, a lot of things depend on, the design behind collecting that, right? All right, so these are just some suggestions as far as like what we can do or ideas to take into mind. I don't expect any of the groups to like implement any of these things. These are actually kind of challenging to do, but these are things to be thinking about, especially So part of this course is not just you being able to look at stuff, but also to gain some data literacy, so that when you read what the work other people have done, you can kind of ask yourself, does this make sense? Do I trust their analysis of the data here? Okay, so so these are things that, again, having a true randomized experiment might actually be tough to do. But can you still draw cause and effect conclusions if you don't have a truly randomized experiment? In limited ways, yes, but it requires some thinking and some maneuvering here, okay? So let's say you want to kind of study like the effect of flu vaccines on flu infection rates, right? So like I think in general we say like, oh yeah, the flu vaccine is effective, but like you really want to kind of study, what difference does it make and things like that. If you wanted to perform a randomized experiment, that would actually require you to randomly assign people, and some people would get like the actual vaccine and some people would get placebo or something. But this would kind of like, you're basically forcing some students to be vaccinated and others not to be vaccinated and things like that. And there's, ethical concerns with that. So instead, you just have observational data, all right? And you can record like who got vaccinated, who didn't get vaccinated. You can so you have to kind of fully define who all of these people are, right? So, you pretend like you're running a real randomized trial, but then you have to think about like, okay, who counts, who doesn't count, what is the outcome I'm looking at, even though I just have observational data, okay? So you say, all right, who's part of my experiment? When does the clock start? That's your time zero. What counts as a treatment? What's the outcome that you measure? So you might say, okay, we're going to just limit ourselves to students living in dorms. We're going to say start at the fall quarter. The treatment is whether they got a flu shot or not. Do they still have like flu shot clinics and stuff, the campaigns and stuff? Yeah, I recommend it. Okay. And then the outcome will be like who actually tests positive for flu and stuff like that. Okay. So this is how you kind of think about it, and this is going to kind of filter down your data to a set that you can kind of work with, okay? And then you have to start adjusting for these confounding effects, okay? So confounding effects are these other variables that influence both of the things that that you want to try to control for, right? So there might be a confounder like the notion that somebody's more health conscious, okay? So that people who are more health conscious might be more likely to get the flu shot and are also more likely to like wash their hands and do these hygienic things that perhaps reduce the risk of flu and stuff like that. And can you control for that? Ideally we can, okay, but sometimes we can't, right? But you want to try to make your groups, the treatment and the control group, kind of look as similar as possible as far as these different confounders that you've identified, okay? So you match your groups as much as possible. You make your treated and control groups look as similar as possible. You can also, what we call outcome regression. You can try to predict the outcome while controlling for some of these confounders, right? So you take the confounders and you use them as predictors themselves to try to control for these things, if you're even able to measure some of these confounding variables, okay? If you do both, okay, then you really only need to rely on one of these things, okay? So you can take your vaccinated students and unvaccinated students and try to match them up in terms of, similar age and prior illness and things like that. Because, prior illness, if somebody got the flu last year, maybe they're less, I don't know what the rules are, okay? So you have stuff like that. All right, so anyway, we're out of time. These are ways you can try to account for things that, even if it's observational data, you can try to make cause and effect things, okay? Sometimes we have these what we call quasi-experiments or natural experiments, where there's just kind of like a natural difference that happens, like there's like a rule change or something like that, okay? And that could end up being kind of like a little bit of a natural experiment. So you don't get to control that, but you know, for example, if there's like a eligibility criteria, right? You say shots are free for students under age 20, and then and those and not for those who aren't. And so you can kind of just look at, is there a difference as far as those who are just under age 20 and those who are just over age 20, and see if there's some kind of difference there, okay? Because, you know, and the grand, you know, if you look at the full spectrum of ages, there might be age might be related, okay? But if you just kind of look at this narrow band where you just know there is a difference here, that could lead to something, right? All right, and then there might just kind of be these natural differences. One dorm could run a vaccine campaign and another doesn't. And, you know, these are kind of like proxy variables, okay? And things like that, okay? And you could try to set up matches and things like that. Okay, so that's the ideas behind trying to draw cause and effect conclusions from observational study. And then on the other hand, another part is trying to generalize to the population if you don't have a random sample, okay? So if you don't have a random sample, but you want to generalize to the population, what can you do? You can try to, what we call, take your sample and, you know, reweight things, okay? Based on what you know about the population, okay? So let's say the data you have, okay, doesn't quite match the population. So let's say in the population, this is wrong. Maybe at a smaller school, but like 40% of students, okay, are first year students, but only 20% in your sample. Then what you're going to do is you're going to reweight what happens in your sample so it matches the population. Okay, so you give you try to you can either resample, downsample, or just reweight your values, okay? You can also kind of set up little diagrams to try to figure out how people end up in your sample, okay? You ask yourself, you know, why are these people in my sample the ones that ended up in my sample, okay? So again, in the ideal scenario, we have a random sample, okay? But then you look at the actual sample you have and you say, how did these people end up in my sample, okay? What variables, treatments, and things like that end up causing somebody to be part of my sample, okay? And then, and if you find that there are factors that affect who's in your sample, and also the same factor affects the outcome, then you won't be able to generalize, right? So if you say, okay, the reason why people ended up in my sample is because, I don't know, they were interested in this thing in the first place, and one of your outcome variables is what is your interest level, okay? You can't use your sample as a way to draw conclusions about your interest level, right? The interest level thing is directly related to who ended up being part of your sample, okay? But perhaps other variables aren't related to that, and then maybe you can draw a conclusion there, okay? All right, so anyway, this is just some stuff there, and then this, and then I have questions to ask about any data set. This aligns a lot with the questionnaire that you will be filling out when you pick your group project data and things like that. But these are just things that you want to be thinking about and asking about the data set. So anyway, we'll end there. I got office hours. Oh, your last view quiz answer. Last view quiz answer is the letter A. A as in apple. A as in apple. All right, we'll end here. Have a great rest of your day. We'll see you Wednesday.